jet off after this. So today I thought there's two options. We can either one, go through the 2019 past paper. Is that legible for people? Yes. Or two, can go through some random questions from different sections. So do people have a preference whether they would prefer to go through an entire past paper and kind of look at how we'd tackle it, or if they'd actually prefer to focus on specific questions and specific concepts? All right. So we're going to go through the 2019 past paper and can potentially LaTeX up the notes for the other questions afterwards and upload those. No, how do I do a new page? Okay. Again, we're looking at 2019. So this one was split up into 4 questions. So you've got 2 on Adam's part. So finite dimensional quantum mechanics. And 2 on, at the time, well, what is now Peter's part. So infinite dimensional. And so in the paper, it says that it's out of 100 marks. And if you look, you've got question 1, it's worth 20 marks. Question 2 is 30 marks. And then both of Adam's questions are 25 marks. And if we look at Adam's section, a lot of it is just short answer responses, whereas the first 2 are pretty involved calculations. So as just an exam technique, you've got 5 minutes reading time or 15 minutes reading time or however long at the start of the exam. So you should be using that to look through, work this out. And then where do you think it's easiest to pick up the quick marks? Adam's section, right? So probably do this bit first and then come back and do Q1 and Q2 because it's equal marks, but not equal difficulty. We're going to do Q1 and Q2 first, though, because they're good warm-up exercises and because the whole point of this session is to do the more difficult stuff. So question 1, we're told. I should start recording this, actually. Oh, it is recording. Sweet. We're told we have a particle of mass m. Is in a simple harmonic oscillator. So you should know the Hamiltonian for that looks like this. Where this is the frequency. And at time t equals 0, we have the wave function. Does anyone recognize what this wave function looks like? Yeah, so if this was the ground state, what would sigma squared be? So we've already got a 2. So not working in natural units, well, the natural units of the system. Luckily, we've got a formula sheet which tells us that for the ground state, we have sigma squared equals x naught squared equals h bar over m omega. Okay. And so the first part of question 1 asks us, what is the probability that when we measure this, we get an energy of h bar omega on 2. So what do our energy levels look like for the harmonic oscillator? What goes in this bracket? Yep. N plus a half. So if I'm looking for the state where I have energy equals h bar omega on 2, what state am I looking for? N equals 1 or n equals 0, right? So like we said, we're looking for the ground state. Which we know has the wave function and they tell us that x naught is, well, I'll just circle it. Okay, so if I want to determine the probability given an arbitrary wave function, what do I have to do? Yeah, right. So like this psi x0 can be written as some sum of the individual energy states, right? Familiar with this? Just writing it in the eigenbasis of the harmonic oscillator. And so if I take an inner product with psi naught, then from this expression, that should give me Cn, right? Because only, I'll see 0. Because it will basically only pick out the sigma naught component or the psi naught component. So how do I evaluate what this inner product is? Right? It's going to be integral of psi 0 x star. We can plug in Does anyone know how to evaluate this integral? Yeah, correct. So the correct answer is we read it off the formula sheet. And so the formula sheet tells us that the integral of e to the negative x squared a dot dx equals square root of pi on a, right? So from before, we know our a is going to be 1 on 2, 1 over sigma squared plus 1 over x naught squared. I'm going to write as and so this integral comes out to square root of, who's going to go up the top? X naught squared, sigma naught squared is going to go up the top. We've got our pi, and then we have x naught squared plus sigma squared. I don't know why I keep running naught. And then what was our prefactor? It was 1 over pi squared, x naught squared, sigma squared, the 1 on 4. And so I'm going to write this as, am I doing that right? All together. So this goes to 1 on pi to the 4, x naught to the 4, sigma to the 4, a half. So now I can multiply these together, and it's 2 x naught squared, sigma squared, pi over, have I done that right? Ooh, so that should be, go back. That's right. Oh, I've just written it differently. Yeah. So I can actually write the prefactor as this, which is nicer. And so that should simplify down to 2 sigma x, I don't know why the line is being weird, over sigma squared plus x naught squared, like that. All right, and so the question then, I'm going to rewrite that because that looks awful. So our final answer is that the probability that E equals h bar omega on 2 is given by square root of 2 x naught sigma over x naught squared plus sigma squared. So the question then asks us, when is the probability of this energy being the ground state going to be equal to 1? So what did we already notice about the original wave function? I think Fletcher, you said it, right? Yeah, it looks like the ground state, right? But we've got a different width. So when would we expect this to be equal to 1, right? When sigma equals Remember we had psi 1, psi 0, and our psi was right. So when would I expect the probability to be equal to 1? When they're the same wave function, right? So that would be when x naught squared equals sigma squared, right? So x naught equals sigma. And is that what we get? We get, if we plug it in, we get 2 x naught squared over x naught squared plus x naught squared equals 1. So we're good. Okay, so the next question is all about ladder operators. So for the next part, it's all about ladder operators. So how comfortable are we with ladder operators? Love them? Good do. So the ladder operators are given to us as a plus minus equals 1 over square root 2 h bar m omega x minus plus IP. Okay. And so we know that if I have a plus acting on the nth state, that gives me the square root of n plus 1 prefactor and then takes it to the n plus 1 state. And if I have a minus acting on the n state, it gives me a square root n prefactor and takes me to the n minus 1th state. Right? Like a ladder operator. So we have n plus 1. We go up with a plus. I shouldn't write it like that because that looks like an adjoint, even though they are. And I can go down with a minus. Is that all cool to people? Comfortable with that? Okay, so now the question asks, so knowing these, we want to calculate x, p, and x squared for an arbitrary stationary state. And so we don't want to, or we shouldn't have to actually look at what the wave function is. So the first step is we want to express x in terms of our ladder operators. Can anyone see how you can do that intuitively? Not quite. There's a little bit more steps. So like if I rearrange for this, right, I have x equals, I'll leave the prefactors there for now. A plus minus, and then plus minus IP up to some constants, right? So I've still got 2 simultaneous equations, right? Yeah. But if I look, I can see that x always enters positively, but p enters, it changes the sign, right? So if I just write a plus a minus, then this will give me 2m omega over square root 2 h bar m omega x, right? Which gives me square root of 2m omega h bar x, and then I can just pull it over to the other side. So we've got this expression now. And so if I write my x, this is now going to be expectation value of h bar 2m omega right? And so what does this look like for the nth state? Do you remember what a expectation value looks like? Yep, but we're not working with an explicit representation of our wave function, right? All we know is that our wave function is this ket n. Right? But let's intuitively think about what it should be, right? So when an operator acts on a state, it tells you, if I write my state in terms of all its eigenvalues as the eigenvectors, right? And then I act on it with some operator A. This goes to Cn. These are the eigenvalues. Which we know is basically gives you the square root of the probability, right? Like if I square this, well, this is the measurement, sorry. So this is what I might measure. And this here, if I square that, right? So if I'm trying to work out what the expectation value is, that's what the average value I should see if I keep running this experiment, right? So basically I need to convert this into something that looks like a normal expectation value, which is sum over your probabilities, or sum over your outcomes, where it's a probability of n times whatever the value of n is, right? How do we do that in quantum mechanics? Well, the only way that we really can is we hit it from the other side with our other state vector, so the conjugate. This is psi. I write that the same way. Right? And this looks like what we said before, right? Is that all good? So if we go back now to this expression, and we're talking about our state being some vector or some state n, what is the form of this expectation value? What do I put in here? Yeah, this is our wave function, right? So this is just n. Okay. So now what happens when A minus acts on n? Yep. And when A plus acts on n? Yep. So I'm going to get something that's proportional to n plus 1 plus n minus 1. So what is this going to be? They have coefficients. It shouldn't matter, but just looking at those inner products. So I've got the state n and the state n plus 1 dot producted together. Yeah, right. In quantum mechanics, we always assume that all of our states are orthogonal, right? All of our stationary states are orthogonal. So that's 0, and this one is 0. Okay, so P, what form is P going to have? Yeah, it's going to be something proportional to something that looks like a plus minus a minus, right? Because we had that a plus minus is basically looks like x plus minus IP, right? Modulo signs. So by comparison with the expectation value of x, can we say something immediately about p, the expectation value of p? Yeah, right? Because the minus is going to lower the state, the plus is going to raise the state, but the other side is still the same. So this is, again, is going to immediately tell us that it's going to be 0. The question then asks us to verify that this agrees with Ehrenfest's theorem. So are you guys familiar with Ehrenfest's theorem? Is that covered in the course? Forgotten it? Okay. So Ehrenfest's theorem states that if I have some operator, its expectation value evolves according to this equation. Yeah. So this is, let's clarify. So this is a number. This is an expectation value. Then we've got the commutator. And again, we're talking about the expectation value of the commutator. Because this commutator, right, is h psi minus psi h. So this is still an operator, still a big matrix. So if we're talking, exactly. If you want to do it in its like full glory, it's like, so d dt of psi omega psi equals psi dot omega psi plus psi omega dot psi plus and then you play around with Schrodinger equation and you get Ehrenfest's theorem. What you're referring to is this term here, right? Which in Schrodinger picture, typically that's, you don't have a time dependent operator. So this is 0. Yeah. Yeah, that expression probably looks complicated, but it's literally just the product rule, right? I just differentiate each of my one at a time and leave the rest untouched. So if we're talking about the harmonic oscillator and P, I'm going to have dp dt equals I h bar expectation value of HP, right? What's the left-hand side? 0? Yep. Time derivative of 0 is 0. Okay, and then what is HP? Right, do we remember what H is? The harmonic oscillator? Yep. What do you mean? Times d. So if I'm talking about just in terms of the operators, yeah, this is plus half m omega squared x squared. If I explicitly go to the x basis, then you've got p goes to negative I h bar d dx, and x goes to x, right? Yeah, and so in that case, then you get negative h bar squared over 2m d squared dx squared. Okay, again, pen's gone funny. Plus a half m omega squared x squared, right? Yeah. Is probably what you're more familiar to seeing in class. Okay, so there's only 2 commutation relationships that we should need to know here. What's the first one and what's the second one? What are the two operators in this equation? Yeah, I've got a p squared, right? And what's my other one? X squared. What's the commutator of p squared p going to be? Yeah, right? If a thing automatically must commute with itself. What about x squared p? Do we remember what this one is? Yep. This is canonical commutation relation. So if I have a product, x squared p, I can use this expression. Right? And so what does this give me? 2 IH bar, right? Yep. X. If I don't remember that relationship, how would I work it out in an exam? Yep. X squared p, I'm going to put it on some test function. It's going to equal x squared. The main thing is this is going to act on everything to the right of it, right? That's the x squared and the f. I can see when I act on the f, I'll get the same as the first term, right? The x squared out the front, but the different sign. But I also get a term from differentiating the x, which is 2IH bar x f, right? That cancels off with that. And I have the x squared p on some test function f equals 2IH bar x times that test function f. So I can identify these two components as being each other. Okay, so now we have that 0 equals IH bar expectation value of 2IH bar x, which again should come down to minus 2 x equals, what did we say about x, the expectation of value of x? 0, right? So that's 0, which is what we expected. Got left-hand side equals right-hand side. So we're good. And so the last one that we had to find was x squared. So this is going to be proportional to, because since I care about this one, I will actually write out what the constants are. So when I square this, what am I going to get in my brackets? So yeah, but what's a plus plus a minus squared? That's the first term. Do I have a 2 out the front of this? No? What do I have instead? Yep. Good. So that's the main thing to remember, is that when we're dealing with operators that don't commute, we can't say that a squared plus b squared equals a plus b squared equals a squared plus b squared plus 2ab. We actually have to remember that you're going to get all the actual permutations. The easiest way to do it is if you just have it like this and remember to go that, and then you move along and do that, actually just physically do the multiplication. Okay, so is this going to be 0? Two terms up there are going to be 0. Which two? Yep. Is that what? Yep, for the same reason we said before, right? They lower the state and it's different to the other state. But what about these two? Not necessarily going to be 0, right? Because the first one is going to take a state down to n-1, and then it's going to bring it back to n. The other one will take it up to n+1 and then bring it down to n-1, and back down from n+1 to n+1 minus 1 equals n. But we know what our actions are. If I write this out explicitly, I have got n, a plus a minus n, plus n, a minus a plus n. What does a plus do when it hits the n state? Yep, and what's the prefactor we get? Yep. So this will go to, and I'll give you the other one for free. Hey, does anyone want to give me the last line? No? So when a plus hits n-1, it's going to give me a prefactor of n-1 plus 1, right? Square root. And when a minus hits n plus 1, it will give me a prefactor of square root n plus 1. Right? So I get h bar over 2m omega. Now I'm going to get an n from this one. And from this one, I'll get an n plus 1. So overall, I'm going to get 2n plus 1. So this is my expectation value. What can we say as n increases? So as you go to higher and higher energy states, x squared increases, right? So what's physically going on? As x squared increases, I'm finding that my particle spends more time out by the boundaries, which is what you expect classically, right? If you look at an oscillator, you should find it at the turning points because that's where it's slowest. And then the last one is the fun one because we actually have to look explicitly at what our states look like. And this asks us to, knowing the action of a plus and a minus, and we know that psi x0 equals this form, right? We want to use this to derive a form for the first excited state. So if we want to get to the first excited state, what are we going to do? Yep, so we know this. What's my prefactor going to be? Yep. And what's the form of a plus? So minus IP. So when we go to the x basis, this is going to be m omega square root m omega to h bar x minus, that goes to plus. No, stays as a minus, so we pick up minus IH bar. And all this is going to act on psi naught. Okay. And now I'm just going to leave it in terms of x naught and then come back to it. But so the only thing that we really need to worry about is what this derivative is going to do, right? When we hit this with a derivative, we're going to pull down a factor of 2x over 2x naught squared, right? With the minus sign. You can see that. So this comes out to square root of m omega 2 h bar x minus h bar 2 m omega. And then we have our minus 2x over 2x naught squared. So they cancel. And then we're still left with the psi naught term out back. From here, it's just algebra. So I don't really want to go through it all, but you should end up with something that looks like m omega pi cubed h plus minus a couple of factors of 2. Does everyone follow that question? Yeah, so the main thing is just using the operator and using that a plus 0 equals 1. Right? If I wanted to do this for the second state, I can do it again, right? I have a plus 1 equals root 2, 2. And so I just need to remember to divide through by 2. Okay, so that's harmonic oscillator. Basically, if you get asked about it, it will be some form of ladder operator stuff because that's the interesting thing from it. So did anyone have any questions from that section? Anything that they wanted to go over again? Oh my God. Should be all you need to know about the harmonic oscillator from an exam point of view. So it's basically all you can get asked. All right. Okay. Are we feeling all warmed up now? Yeah, cool. Okay, so now we're going to do a little bit of a little bit more involved problem. We're actually going to solve the Schrodinger equation. So we're told that we have a potential that looks like this. So Vx equals infinity for x less than 0, negative V naught for 0 less than x less than a, and 0 for x greater than a. Wait, sorry, how did we get the negative 2x to x naught from root 2? Yep, I'll just go back. So we've got this derivative term here. So this d dx, right? And that acts on this part of the wave function here, is an exponential. So if I write it out in all of the overdone glory, so that's d e to the negative u du dot du dx, where u equals negative x squared over 2x naught squared. Have I dropped a minus sign? No. Sorry, this doesn't help. Right. This is just going to be negative e to the minus u, standard integral, standard derivative. And this is then going to be 2x over 2x naught squared, right? Because x naught is just a constant. And so I've just replaced the derivative term in this expression here with the actual derivative. And because I'm talking about an exponential, I still get the same wave function back. And so I can just leave it sitting on the side. Does that make sense, Nina? Awesome, no problem. Okay, so jumping back to this question. So we've got a well of width A and depth V0. We have an infinite potential wall, and then we have just free space. So just this is V equals 0. And so the question is asking us to give the transcendental equation for the energy of the bound state in terms of the other physical variables. Okay, so when we're talking about bound state, what does that mean? Yeah, exactly, right. So we want the particle to be confined to some part of space. We don't want it just being a free particle and flying off. If I have sufficiently high energy and I sit above this barrier, right, I will fly in, bounce off the wall and just fly out. But if I have low energy, then I can in theory be confined somewhere within that well, right? And so we have that E is negative, and we have that negative V0 less than E less than 0, right? Negative V0 is the bottom because if we put it under the well, then it's just going to be flat, right? Put it in, if we put the particle in so that it's in a wall everywhere, then there's no particle. Okay, so we've got 3 regions. So we've got region 1, region 2, and region 3. So in region 1, what's our wave function going to be? Yep. Okay, what about region 2? We've got h bar squared so if I move everything to one side, apart from the second derivative. Okay. So what do I know about this number here? Yeah, but more importantly, what do I know? What can I tell about this? What about this, the sign of 2m e plus v naught h bar squared? Right, so I've got this, right? So if I add v naught, I've got 0 less than e plus v naught less than v naught, right? So this is positive. So I've got negative times some positive number psi, and it's a second derivative. So if I say let k equal square root of 2m e plus v naught over h bar squared, then my wave function, like you said, it will be oscillatory, and it will look like a e to the I kx plus b e to the minus I kx. You can also write this as up to you. Now, what if I look at the third section? So I don't have this v naught term, right? So I've got the second derivative is negative 2m e h bar squared psi. Now what can I say about the sign of 2me over h bar squared? Right? This is less than 0, right? We said that. So this thing here is negative. So this whole term itself is positive, right? But if we write this as E equals negative 2m, it's easier way. So I can write it like this to make it clear. And so I define kappa as square root of 2m absolute value of E over h bar squared. Okay, and so this now is going to have the form right? There's no complex term. So if we're dealing with the bound state, and this is describing region 3, so as x goes off to infinity, what can we further say about psi 3? So what happens as b goes to, as x goes to infinity, right? This goes to e to the minus infinity, which goes to 0. So this term's fine. What about the first term? First term though, this goes 4. So we've got that a equals 0. So we've got that psi 1 of x equals 0. Psi 2 of x equals a sine kx plus b sine cos kx. And that psi 3 equals c e to the minus kappa x. Right? First constraint that we're going to use is, so we want continuity of the wave function, right? Should agree at every point in space and time. So we should have that 0 equals psi 2 0 equals b. Right? Because sine of 0 is 0, cos of 0 is 1. So this tells us that b equals 0. And then we have at a, so where our well ends, psi of a equals psi of 3, psi 3 of a, which tells us that c e to the negative ka equals a sine ka. And so I can say that c equals a sine ka e to the kappa a, right? So I've used all my continuity constraints. What are my next set of constraints that I can use? Yeah. So how many continuous derivative constraints are we going to have? Yeah, just one, right? Because we've got an infinite potential wall, so that's not going to count there. But the derivative of psi 2 of x is going to be ka cos kx. The derivative of psi 3 of x is going to be negative kappa d e to the negative kx. Now I could use that expression, but I don't need it at the moment. So just for succinctness, I'm just still leaving it in terms of d. Sorry, d should be c. I've changed it from my notes. Right. So I'm just saying, like, I could use c equals a sine ka e to the kappa a, but I don't need to at the moment. So just to keep it shorter, I'm going to leave it. And then just equating them, I get that Ka cos A equals negative kappa, and now I'll put it in A sine Ka e to the kappa A e to the minus kappa A, right? So they take each other out. And so I can take out my A's, right? I've got an A on both sides. And so I can say that negative K on kappa equals tan K on A, right? Does this look familiar to anyone? Seeing some nodding heads. But this should look like your one of your constraints for the finite square well, right? You get something like K tan Ka equals, or kappa. And then you should get modulo minus signs. Right, and so this is our transcendental equation. If you want to be explicit, we can substitute back in what K and kappa are, put in our actual E's and stuff, but that's just algebra, so I'm not going to do that. So is that all clear to people what we did? So we just wrote down our wave function in our different regions. Then we used our constraints to eliminate as many of these free parameters as we could. And then that left us being able to write all the variables together in a transcendental equation. So this is something that we can't progress any further with. We can't get analytic solutions out of it. You do it numerically, but that's the solution that you need. Okay, so last one of the real Schrodinger types, and this one's going to be fun because it's a bit different to what you've seen. Have you guys done the Dirac delta potential in class? Yep. So we're told that with this case, we're told that we've got an infinite potential wall again at 0.0. So this is x equals 0. And we're also told that at x equals a, v of x equals negative v naught a delta x minus a. So we got a Dirac delta. So I'm not going to bother. Oh no, did I? Yes, I did. So we got three regions again. We've got 1, 2, 3. And again, we're trying to find the transcendental equation for the bound state with this delta potential. Why can't I write, like, just solve the Schrodinger equation exactly on x equals a? Yeah. Just you can't, yeah, you're talking about a distribution. It's only defined in the sense that it's being integrated over. So again, we got psi1 of x equals 0, standard stuff. But now we're talking about the bound state, right? So again, what do we say about our energy? Yep. Here and here, there's no potential, right? In region 2 and 3. So from before, what do we know about the form of our wave function? Right? So we said that E was negative. And so in region 3, I'll then get C. Can I get rid of any of these terms immediately? Yep. Stop chopping the pen. I can get rid of this term for the same reason as before. As we go to infinity, that will blow up. But I can't get rid of the D term, right? and I can't get rid of either term in here because it only goes from 0 to a. So everything stays square integrable. Again, we're then going to apply our constraint that at 0, this is equal to 0. So we have 0 equals a plus b, right? From psi1 of 0 equals psi2 of 0. Just exponential of 0 is 1. So I can rewrite psi of 2 of x as a e to the kx minus a e to the minus kx. Does anyone recognize what this is? Up to some prefactors. Does that jog people's memory? Yeah, should be 2, I think, out the front. But because we haven't defined what a is yet, it's still just an arbitrary constant. I can just chuck that prefactor in a and call that new thing a. So I'm just going to do that. And then we're still going to have continuity here, right? The wave function is still continuous everywhere. So we have that psi2a equals psi3a. So a sinh ka equals, is that the one? Yep. D e to the minus ka. And so I can say that D equals a sinh ka e to the kappa A. All right. So I've got a delta potential now. So can I use the same continuity of the derivative argument at A? The answer is no. If you think about it, you got an infinite jump suddenly. So your derivative is basically flat, 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 full. And then on the other side, it will immediately infinitely jump back up, right? So very much not continuous. But what we do have is the Schrodinger equation, which tells us right? So what could I do with this? So it's not an easy trick if you haven't seen it before. But if I integrate in a tiny ball around A, I get this expression, right? All clear? So if I take, as I take e to 0, or epsilon to 0, what's going to happen to this right-hand side term? So the wave function's continuous. Yep. So that will go to 0. Are all the K's kappas here? Yes. If I'm switching between them, they're all kappas. Okay. And so what's going to happen to this term? The potential term. So we're integrating over a Dirac delta, right? And we're integrating around A. So this, the Dirac delta, right, is defined as basically right. Otherwise, it's why it's sometimes called the sampling function or sampling, because it effectively picks out the value of a function at one point when it's integrated over. And so we're always going to be integrating over it, even as we take that limit really, really small. So we have that negative V naught A delta x minus A psi of x will go to negative V naught A psi of A, right? We have two choices in theory here, right? We've got psi 2 or psi 3. Does it matter which we choose? No, right? Because we've already enforced continuity. They're going to have the same value. So I'm just going to choose phi 2 for fun. What about this term here, right? We've got negative h bar squared 2m of A plus epsilon, A minus epsilon of, I write it in a little bit more of a suggestive way. So if I just forget about taking the limit to start with, what's this going to give me? So I'm integrating over the derivative of something. Yeah. Right. And so talking about a sufficiently small epsilon, what branch is this going to sample? Psi 1, psi 2, or psi 3? Yeah. And the top one? Mm-hmm. So what happens when I take epsilon to 0? Right. So if I take epsilon to 0, should it? Because I've got derivatives, right? Not dealing with this thing, but I'll get this expression. And so if I put everything together, I have negative h bar squared on 2m psi dash of 2 of 3 evaluated at A minus psi dash 2A equals, and I'm going to move this potential term to the other side. Right. And then the derivative, where did I put my expressions? Right. So the derivative of this is going to be kappa cosh. And the derivative of this is going to be negative kappa DE negative kappa A. This one. Yeah. So when I go down and get h bar negative h bar squared on 2m kappa A cosh K A plus kappa D e to the negative K A equals V naught A, which is kappa A sinh. Okay, we know what D is, right? We said that before was A sinh kappa A e kappa A. And so this looks quite similar to what we had before. This is going to cancel out with this. And we get negative h bar squared on 2m. A, I'll pull out the front. Kappa cosh kappa A plus kappa sinh kappa A equals B naught A kappa A sinh kappa A. So I can get rid of all these A's and kappas. And then I'm going to put all the sinh terms together, and I'll leave the cosh ones over here. So I have negative h bar squared 2m cosh kappa A. Why is my screen glitching? Equals negative 2m v naught h bar squared sinh kappa A, and then I'll get, no, why have I done that? That is jumping ahead of myself. Okay, h bar squared on 2m plus v naught A sinh kappa A. Okay. And now I get to divide through by cosh. And so we can put it in a form that looks very similar to what we had before. So I'm going to move the prefactors to one side, and I'll put my trig expressions on the other. And we get negative h bar squared on 2m 1 over h bar squared on 2m plus v naught A equals tanh kappa A. Again, modulo minus signs. All right, and so again, that's our transcendental equation. We can substitute back in for K if we want, but that's fine. In an exam, I would either substitute in or just write again where K equals something like that, so that you've got it at least clearly in the variables that the question asks for you. All right, so that's all the Schrodinger equation questions from the paper. That's probably the harder section of the paper. Did anyone have any questions about that? Why was there a K on the right-hand side? Back a bit, sorry, it's not a derivative. Maybe because I accidentally put one there. Yeah, because I accidentally put one there. Yeah, so this one's not here. So they'll stay there. that should be fixed up. That should be them all in the right spot. All right. So no questions about that part? All good? So Schrödinger equation. So you want to remember to split into sections and write the wave function for each. Consider your boundaries. So like as x goes to plus minus infinity, psi of x has to go to 0. And then the main thing is to remember the sign of E, right? So remember before we had things like E plus V naught was greater than 0, and that led to oscillatory solutions. But if you have E less than 0, for example, that goes to Kx, where you have rising and falling solutions. And then, of course, again, it's just apply, match up at the boundaries. So you have psi x is always continuous. And psi dash of x is continuous aside from points of infinite potential. So that's where you have to do funky stuff like with the Dirac delta. We saw we actually had to play around with the Schrödinger equation. All right. So that's part 1. So that's done. Any questions about any of that section at all? Nope. Cool. We feeling confident with that? Fairly so. Okay. So now we're going to get on to Adam's section. So if you might have seen, Adam likes to give you a lot of verbal questions. So I probably will stick to the more mechanical ones. Okay, so we'll go through question 3. Again, this is just a list of questions. Okay, so everyone should be able to tell me this. What is a basis for a vector space? Okay, so we're jumping ahead. So a basis at its thing is basically it's just a set of vectors, right, that we can use to describe any other vector in the space. And we want that to be in a unique way. So the 2 conditions we have is that it is spanning. So every vector can be written in terms of a sum over the basis vectors and linearly independent. Which is basically this sum should be unique. Okay, and then so the next question was, so we generally use a basis that is orthonormal. And so what are the 2 requirements for a basis to be orthonormal? Yeah, so we have orthogonal. So if I take any 2 basis vectors, say n and m, then their inner product should be this thing called the Kronecker delta. Basically, it's just 1. Well, this is orthonormal. Surely, yeah. Let me rephrase this. So we want them to be orthogonal. which is basically that if I take any two basis vectors that aren't the same thing, then this should equal 0, right? Which is effectively a way of saying they're perpendicular. And if they're normal, then that means that they're of unit length, so that this is equal to 1, right? Because this is basically the length squared. You can write that all as one condition, which is nm equals nf. Where this thing's called the Kronecker delta. You're all familiar with Kronecker's delta. Basically, it's just defined as equals 0 for n does not equal m, 1 n equals m. Okay. And so a student then says, when a linear operator L acts on an eigenvector lambda, the resulting vector is parallel or anti-parallel to lambda. Is this true or false? Yeah. So L hat of lambda, right, equals this, right? And this is just a number, so it can't change direction apart from flipping it if you have a minus sign. So it's, yeah, parallel or anti-parallel. Is the integrate in tiny interval method always how you solve infinite potentials? Are there any other funky tricks? Lol. It's one of the common ones that I'm aware of. There's probably other more elaborate techniques. But yeah, there's lots of tricks people come up with for solving difficult problems. But yeah, it's only one really I would expect to see in a second year course. And only if they'd shown you it in the Dirac delta in class. Okay. So now we're going to say that L hat equals -1, 1, 2, -4. And it asks us to find the two eigenvalues lambda1 and lambda2. So can anyone tell me immediately what the eigenvectors or eigenvalues are? What was that? Ooh, not quite. So the easy trick when you've got a 2 by 2, so you've got that this holds all the time, but it's easy when you've got a 2 by 2. So you can either do the whole -1 minus lambda -4 minus lambda -2 equals 0 characteristic equation method. When you're dealing with a 2 by 2, you also have that the determinant is equal to the multiplication of them. So this is 4, that should be a -1, plus 2 equals 6. And that lambda1 plus lambda2 equals -5. Can anyone see what the eigenvalues are going to be immediately from that? Yep. This is something you just get better at when you do it all the time. Okay, and then it's going to ask, say, find the eigenvectors. So for the -2 case, I get this goes to 1, -1, 2, -4, -2, -2. I only need to look at the first line because it's 2 by 2. And I know the second line is just going to be a multiple of the first line, right? Does that make sense to people, or is that a bit of a leap? So like normally, right, you do matrix reduction on this and then try and write like x1 in terms of x2 or something, for example. If I'm dealing with a 2 by 2 matrix, I know that each row isn't going to be linearly independent. And because there's only 2 rows, it just means they're going to be multiples of each other. So I can just straight up just look at the first line straight away, which tells me that x1 minus x2 equals 0. So this should have an eigenvector of that. Got that right? Right. Because if x1 is 1, then x2 has to be 1 as well. And then I've just normalized it. Now, if I look at the other one, this will go to 2 minus 1, 2 minus 3 plus minus 3 minus 1. So again, you can see even clearer now, the rows are exactly the same. So I have that 2x1 minus x2 equals 0. So if I set x1 to 1, then x2 is going to have to be 2. So my unnormalized is going to be 1, 2. What's the normalization coefficient for this going to be? Yep, it's just sum of the squares in square root. Then the next question just asks you to demonstrate the anti-parallel stuff. I'm guessing you all can do basic algebra, so I won't go through that one. Okay, and so the next one says, so it tells us that operators are represented by Hermitian observables are represented by Hermitian operators in quantum mechanics. So what is the one key requirement of observables that requires operators to be strictly Hermitian in quantum mechanics? Yeah. So we need them to be real. And so we have that for a Hermitian matrix, H dag equals H, right? If I write this in the eigenbasis of each one, then I have that this is like lambda 1, blah, 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 down to lambda n. So if I take the adjoint of this, is to lambda 1 star, like this. The only way this can be true is if they're real. So that means all of our observables are real, which is nice because observables should be physically observable and we can't observe complex numbers. Okay, so the next question asks, is probability an observable? No, why don't we think it's an observable? So what would an operator for probability look like? Yeah, it doesn't really make sense, right? So we can talk in quantum mechanics, we can talk about like the probability current. That's a thing that's conserved and that you can in theory look at and measure, but this is not expressible as a linear operator or a thing. So we say that probability is not an observable. What you could say though is, so if I'm talking about taking a measurement, then that's going to be some projection like this. So if I'm looking at the nth state, this is a Hermitian operator. So I can say that that's an observable. Does anyone want to have a guess as to what that observation would be? So for example, if this is energy, so I have that H is my operator for energy, right? And its eigenvalues are energies. So if I measure something, I get an eigenvalue of H. And so that's an energy of H. But so now, what if I talk about a projection from H? So this is some energy. Right. This is just one of those specific energies. Right. So are you guys familiar much with projection operators? Have you seen this stuff before? Okay. I'll leave you guys to think on that one and come back to it because it's just me rambling and not super relevant to the exam. So I'll continue on. Okay. So again, we're asked L equals -1, -1, 2 minus 4. Is this Hermitian? So what's the Hermitian hermiticity condition? Not quite. So you're missing one step. So yeah, so the adjoint is, so transpose and then complex conjugate. So this is invariant if I complex conjugate it. But if I take the transpose, it's not, right? So this is not a Hermitian operator. Another way that you can tell is, so if it was a Hermitian operator, your eigenvectors form an orthonormal basis. And those vectors are clearly not orthonormal. Okay, so now we're going to consider a three-dimensional vector space spanned by with basis vectors 1, 2, and 3. And we're given the ket alpha equals I1 minus 2, 2 minus I3 and beta equals I1 plus 2, 3. And so the first question is, what are the corresponding dual vectors or bras that go with each of these vectors, each of these kets? Does anyone want to have a guess at B, because it's the shorter one? Beta? Yep, very good. Yeah, so this is the main thing. So you got to remember that when you flip to the corresponding dual, we always have to take complex conjugate as well. Just remember, because for example, we want beta should be real, right? This is the length. So if I didn't, let's just focus on this I equals 1 term, then I would have I 1, 1, I equals minus 1, which doesn't make sense because I've got a negative length. So that's why we have the complex conjugation there. And then, so what do we have for alpha? Got minus I1, minus 2, 2, plus I3. Okay, so now question is to find alpha beta. Which should be straightforward. So we can just look and basically, again, because we're dealing with an orthonormal basis, we just need to pick out the coefficients that are common. So we've got a alpha from here, we get a minus I and then an I here. So that's here and here. We don't have a 2 component in beta. So we then just pick up a 2 and a I, so we get 2I plus 1. Again, looking at beta alpha. Have I? Yes, it should be. I've used the wrong one. Yeah, because this is the. Yeah, because it's minus I minus I2. Okay, and then so if we look at beta alpha, we get minus I again. So that's going to give us a 1. And then if we look at 3, we get 2. No, I had it right the first time. Yeah, I had it right the first time. Minus 2I. Okay, and what do we notice? Alpha beta equals beta alpha complex conjugate. This is a property of the inner product that you should all be familiar with. Is something that you have to use sometimes. Okay, and now we want to find the 3x3 matrix for the operator. Is everyone familiar with what this notation means? An outer product? So you've seen this is an inner product, right? Yep. So that's, if we talk about row times column. If I have a row and a column, what's the other way that I can multiply them together? Right? Can do column, row. Yeah, so this is a matrix and this is a number. So it's easiest to do this question if you just use a vector notation. So this goes to minus I minus 2I. Right. And then the other one is minus I 0, 2. And then I just go first row minus I, so that's minus 1, minus I 0, 0, minus I2 is minus 2I, minus 2 minus I is 2I, 0 again, and then minus 4, and then I minus I. That's right. Is 1, 0, and then 2I. Right. The other way that you can do it, so you can use the method of images, which is if I consider I 0, 2, and I act it on 1, 0, 0, that maps me to some vector, right? Or some matrix, well, a number, which is then multiplied by this. And that forms my first column. If I do 0, 1, 0, that gives me, again, a number multiplied by this, which is my second column. And then if I do 0, 0, 1 again. So you can view each of this as the action of the operator on the first basis vector. This is it on the second basis vector, and this is it on the third. Basically what it maps to. Question then asks, is alpha normalized? So this is alpha here. Very quickly, if I look at the norm, it is 1 plus 4 plus 1 equals 6, trivially not normalized. So the normalized version is 1 on root 6 minus I minus 2I. Okay, and so the next question is V, which is suppose that we prepare the quantum state alpha, we go have lunch and we perform a measurement. What is the probability that we measure 2? That we end up with the state 2. So does anyone want to give me the answer for this? Should be fairly fundamental. So this is my alpha. This is my normalized alpha. Yeah. So that would be the norm of alpha, which would be 1, which would be the probability that if I have a state alpha, I measure it in the state alpha. Yeah. Right. This one, which is minus 2 over root 6 squared is equal to 4 on 6 or 2 on 3. Right. And that makes sense, right? If we look at this, got like 1, 2, 1, so we expect roughly ratio. Okay, and so now the question states, suppose that without otherwise perturbing the system, we now go have dinner, come back and remeasure. What is the probability that we get 1? So there's 2 ways you can interpret this question. So you can either say that we did the previous step and we got the state 2, so we're in the state 2, or you can assume that we did the measurement, got some arbitrary one of the possibilities, then went away and came back and remeasured it. Or just you can just assume that it's in state A because it's a poorly phrased question, which is what Adam tends to do. So I would just state what assumption you're making in the exam. So under the assumption 1, so if we measured it and we got state 2 and we come back and remeasure it, would the chance be that we get 1? Yep, because we're in state 2. So 1, 2 equals 0, right? We're orthogonal. Okay. If we assumed that we measured it and we're in an arbitrary state, right, then we're looking at what's the probability that we measured 1 the first time, which is 1 on 6. And then it will be in that state. It will stay in that state. We come back and measure it. And then that's the same as if we hadn't measured it at all. So yeah, this is actually pretty fundamental. So it's basically the difference between quantum mechanics and classical mechanics. Classical mechanics, right? I have my variables, x and p. I can measure things omega. If I measure it, it doesn't change the system. If I come back, it'll be the same. But if I do it quantum mechanically, now I've changed my system. That part all makes sense to everyone. Okay, question 4. So question 4, we get to see our old friend, the commutator again. So we're told that we have A dag B is a thing called the commutator, and we're asked I minus 2 minus I. Maybe I've been a bit lazy with my minus signs, but yeah, can check. It shouldn't affect the final outcome of the answers, though, because we're dealing with the square. Someone's just asking if I had a sign error before, which is probably true. So what's a mathematical expression for the commutator AB? AB minus BA. Saw that before. So what does it mean mathematically for two operators to not commute? Yeah, but so if I'm talking about just in terms of, so this measures how much something fails to commute. But if I'm actually saying when something doesn't commute, what does that mean I can't do? Yeah, right. I can't have that ABX. I can't map that to BAX, right? So they're different. Okay, and so in physics, what are the implications when we have two non-commuting operators? Yeah, exactly. Because so if they commute, right, I have that AB, and let's say that I'm in some eigenstate of B equals B. This equals AB, B equals BA, B, but that also that BA, B equals BA, B. Right, so B, AB equals B of AB, right? So this AB is a vector because it's an operator acting on a vector. And we've said that it's, you can see that that's the exact form of the eigenvalue expression, right? B acting on the vector AB gives me B times the vector AB, right? So I can simultaneously diagonalize both A and B. And so I can simultaneously measure both A and B. But if they don't commute, then I wouldn't have this expression. I would have the commutator sitting in there as well. And that thing's not guaranteed to also be diagonal as well. In fact, it trivially isn't. Okay, and then you were asked to show that px squared equals 2i h bar px. And this should be very similar to what we saw before. But just to go over it again, you can either use that this is x p x p x plus px x px. And you know that this is your canonical commutation relation. So you get 2 I h bar px from that straight away. Or if you're in an exam, you don't remember, again, do it the test function way. And I'm just going to treat this as d dx squared for now, because it's just a sign and it should all match up. I can add them in later. Again, remembering that this has to act on everything to the side of it. So this is equal to x d squared f dx squared minus d dx, just do it by steps, f plus x df dx. Those two terms cancel out. So this equals negative 2 df dx. Again, that's our expression for p from what we were saying. So this is 2 IH bar px when you just go in and substitute back in the appropriate prefactors. So like here, you would have a negative h bar squared. Again, you'd have a negative h bar squared as well. So this would go to negative h bar squared. So this would go to a plus h bar squared here. And then so you would write 2h bar I minus IH bar df dx, right? This is 1, so I can just add it in. And then that's your proper expression for p there. Did everyone follow that algebra? If there's time, can you explain the canonical commutation relation method? Yeah, so it's just the exact same as what we're doing here with this algebra, right? Like if I did x, px of f, and I work through the exact same way, I will get out IH bar. It's just that you can, a property of commutators is that if you have A, B, C like this, and similarly if it's the other way around, then that's equivalent to A, B, C plus A, C, B. And so it's just, rather than going through the whole test function process and working that all out, it's just quicker if I write this and then use the fact that I remember that XP equals IH bar, which is basically, yeah, what you should remember in quantum mechanics. So it's just doing a little bit of algebra rather than a bit of calculus. Okay, and then so in lectures, it says we obtained a generalized uncertainty principle, delta A, delta B is greater than or equal to I on 2 expectation value of a B commutator. And so it asks us if we can basically get back to the Heisenberg uncertainty principle using this. So again, that means our commutator is XP, which we said we know this is IH bar. So we've got that delta X dot delta P is greater than or equal to absolute value of I on 2 expectation value of IH bar. What's the expectation value of a constant? Yep, just the number itself. And voila. There you go. Right back where we were. Okay, so now it says you can measure P and Y simultaneously with absolute certainty because the corresponding commutator is 0. Briefly explain why this commutator is 0. And it's saying don't repeat algebra if you've already done it. We can just refer back to our previous question. So basically we can go back and we can look at this algebra that we did here, right? For xp x squared. And we can see the only reason we get non-commuting behavior is because this d dx also acts on x, right? So if I'm dealing with py, that's going to be a derivative in y. And so that won't act on the x, right? And I can just pull it through. So this would be x d squared f dy squared minus x d squared f dy squared, right? And so they would commute. Okay, and so now it says suppose the product of two Hermitian operators. So we have a dag equals a and b dag equals b is also Hermitian. So that is ab dag equals ab. What restriction does this place on the corresponding commutator? And again, so we know that this is the conjugate transpose. So this is ab t star. So when we take the transpose of a product, right, we flip the order. And then we take the transpose. This is equal to b dag, a dag. But we know that the individual operators are Hermitian. So this is BA, right? So we have that BA minus AB should be 0. Never done the right way around. Yep, because we also have this, right? So we have that AB dag equals AB and that AB dag equals BA. So they trivially have to commute. And then, so now it asks us to again considering Px and Py, show why they must commute from this perspective of their product being Hermitian. So I can show that if I consider their behavior on some kind of test. So I have psi dag x and y. So this will be a vector now. E dy, pull out my negative h bar. Psi xy. And now I'm going to integrate by parts. So I want to shift the d dy onto the other side. Yeah, because I have to integrate over x and over y. But I can integrate by parts just on the y. Like that's fine. So my surface term is just going to be this, right? Evaluated at the boundaries, which has to vanish. And then I get minus again, d dy which I can write all together as this looks like double integral of I h bar d dy psi x, which I can also put on this side, right? Psi x. So I've got that AB psi, which is this, equals psi AB psi dag, right? Because transpose means I've put it on the other side, and complex conjugate means that this minus I is now an I, right? So this product is also a self-adjoint operator. And so by the rules that we established before, they should commute. Did everyone follow that? Okay, last few questions. Okay, so last one, now we're going to look, we've got two states, psi A equals AU up plus AD down, and psi B is equal to BU up plus BD down. Okay, so the first question is we want to write an expression for psi A tensor psi B in terms of our new vector spaces, basis vectors, which are right. That makes sense to everyone? Seen this before? So this is easy. It's a funny symbol, but it's basically just straightforward multiplication like you've seen before. Okay, and then it says that we also have this singlet state, which is equal to some normalization coefficient of UD minus DU. And so they said in the lectures, you would have seen that this isn't a product state, so we can't write it in terms of something that lives in vector space A and something that lives in vector space B. And the question is, so that now that we want to show that this is true using a different method, which is showing that something called the spin polarization principle doesn't hold. So for spin half particles, you have this spin polarization principle, which basically says your spin points somewhere. So these are your Pauli matrices, sigma X, sigma Y, sigma Z. But for any particle that does not have spin half, this isn't true. So just as an example, photon in theory has spin 1. So you can have it like point up, point down, or point sideways. And that doesn't mean that you can have a net polarization of 0. So it doesn't really have a specific direction that it's pointing. Okay, so you could write out all the Pauli matrices and do it all by hand, but the lecture, the exam actually gives you a table of the actions of what the Pauli matrices do on this double state. And so we're just going to use that. And I'm going to ignore this 1 on root 2 term because it's just a normalization factor and I can add it in later. So we have that sigma X psi S is going to be, I'll put them in anyway, DD minus U. So if I want to take the expectation value, I have to hit this with psi S from this side, right? Which contains UD and DU terms, does not contain DD and UU terms. So this is 0. Psi Y again, referring to that sheet, gives us these terms. And again, that's just from psi y acting on ud and then psi y acting on du. And again, 0 for the same reason. The singlet state contains no dd or u terms. So we're left with phi of psi s is going to then come out to be ud plus du. Because we just pick up a minus sign from the action of sigma z on the du state. Which, if you want to see that explicitly, it's that this sigma z actually equals sigma z 1 tensor the identity on 2 acts on down tensor up equals sigma z d tensor I u equals minus 1 d tensor u. You don't need to worry about doing that explicitly, but it's there. It's an example. Okay, and so then now we need to hit it from the other side with psi s again. So we get 1 on 2, and then we've got our ud term, which will cancel with a ud term, and then we have this minus, where is it? This minus du term, which acts on this other du term, and so we get a minus 1. I'll write that out. ud minus du du. If you want to write it out in all its glory, you'll also pick up a ud du term and a du ud term. Again, they're orthogonal states, and so they're 0. And so, can anyone tell me just by inspection what this expectation value is going to be? Yep, 0, because I've got 1 minus 1. So we have that sigma x squared plus sigma y squared plus sigma z squared equals 0. It does not equal 1, so the spin polarization principle does not hold. And then the very last question of the exam says, comment in 1 or 2 sentences on the significance of the singlet state in quantum mechanics. Do any of you cover that in class? You know what the significance of the singlet state is? It's a few reasons. So it's like what we call like a totally entangled state. And there's a bit weirdness about what that means, but lots of reasons. So singlet state, basically it shows up in a lot of places. So it shows up in ground states of molecules, for example. You often talk about singlet versus triplet states. Effectively, so the idea, right, is you have 2 spin half particles. And so the singlet state is a state in which the total spin is 0. And the other states you get are called triplet states, where the total spin is 1. And so you see this being used in quantum mechanics, well, quantum computing as well. Singlet states for entanglement, all sorts of things like that. But that is the last question in the exam. So yeah, as you can see, Adam's section is a lot of short questions, a lot of just testing your understanding in basic math manipulation. So again, when you do get your exam, I would recommend reading through it in your reading time, identify where the easy marks are, and then do those first, and then come back to the harder stuff that we were doing at the start. Does anyone have any questions from that? But I'm happy to stick around for 5 more minutes before I got to duck off. No worries. No problem, you know. Hope you got something out of it.
Yeah.